Good morning.
Plant is
Good morning, sir.
self-consumption and excess energy is injected to grid. The net metering is available for industries and commercial, gross metering for domestic, but gross and net metering both metering system is available for domestic purpose. But for industry purpose, only net metering is available. They have to consume the electricity, rest remaining electricity, they have to come to the grid. And now the rate is 3 rupees 96 paisa within 10 kilowatt, below 10 kilowatt, above 10 kilowatt, 3 rupees is the tariff. Earlier, when we started this grid connected policy, at that time 9 rupees 56 paisa was the unit charges fixed by a regulatory commission. Solar power plant less than 5 megawatt capacity at rate of 3 rupees 8.
Okay. So shall we start? I think you have received the dates for the internals, is it? When is your BTD?
On 30, sir.
Okay. So the portion is the real gases theory. There are no problems as we have not done it. So how many of you have brought your BTD data handbook? Got it?
Yes, sir.
So make sure after the first law, that is first law theory and problems, we are going to solve the real gas problems, and then we shall move to the second law of thermodynamics. So after the first law, we are going back again to the real gases. By that time, everyone should have the data handbook in your hand in order to understand how to use it. Clear?
Yes, sir.
Okay. So we shall start today's topic. So what is the first law of thermodynamics? We have discussed how it is dealt for the cyclic process, where it says the cyclic integral of heat flows is equal to the cyclic integral of work flows. When you apply for a cyclic process, when you apply the same first law for a non-cyclic process, then you have to apply it as dq is equals to du plus dw, that you have seen. And what else? You have seen the various heat flow equations calculations. Just a recap, of 5 minutes of recap, very, very important. Just listen here. So isobaric process where the pressure is constant, the value of K is 0, represented as horizontal line in an PV diagram. The work done is given by P into V2 minus V1, whereas the heat flow is given as change in enthalpy. For isochoric, it is change in internal energy. For isobaric, it is change in enthalpy. Even the change in enthalpy can be calculated as mCp delta T, that is T2 minus T1. The second process, isochoric process. In this process, the volume remains constant. The value of K is infinite. It is a vertical line in a PV diagram. The work done is 0 in case of isochoric process, as there is no area beneath the process. And the heat flow is calculated as change in internal energy. Remember, isochoric, the change in internal energy. Isobaric, change in enthalpy. Keep this in mind. So isobaric, it is always change in enthalpy, whereas isochoric, it is change in internal energy, that is given by CV into T2 minus T1, mCV into T2 minus T1. If you have m there, you can just add it up there, mCV T2 minus T1. Isochoric, so volume remains constant, that's why it is CV. Isobaric, pressure remains constant, that's why it is Cp. Clear with these two processes? Any doubts? Any doubt?
No.
Okay. Next one is the isothermal process. In this particular process, the temperature remains constant. The value of K is 1, and it is represented as a curve in a PV diagram. The work done expressions are given by 6 different forms. The first form is P1 V1 into ln of V2 by V1. Second is P1 V1 into ln of P1 by P2. The third is P2 V2 into ln of V2 by V1. The fourth is P2 V2 into ln of P1 by P2. The fifth is MRT into ln of P2 by V1. And sixth is MRT into ln of P1 by P2. the coolest part about the isothermal process is whatever the six forms of the work done expressions are there, same can be used in order to calculate the heat also. If you want to calculate heat, you can refer the work done expressions because the heat flow is equals to the workflow in case of an isothermal process. Why and how we have discussed in the last class. Adiabatic process. The adiabatic process here, the entropy parameter remains constant. Entropy is denoted by S. And the value of K is equals to the ratio of specific heats, which is Cp by Cv. The work done expression is given as P1 V1 minus P2 V2 divided by gamma minus 1. Why gamma? Because it is a adiabatic process. If it is not gamma just n, then it would be polytropic process. Now, the strangest part about the adiabatic process is the heat flow is zero. So name the process where the heat flow is zero is your adiabatic process, and the process where the workflow is zero is known as isochoric process. Last but not the least, very, very important, which is the polytropic process. Polytropic process is the process where nothing remains constant, everything will be changing. That's why our value of K would be equal to N. And it is again represented as a curve in our PV diagram. So the three processes which is represented as a curve as isothermal, adiabatic, and polytropic. So all these three processes are represented as a curve in a PV diagram. The work done expression remains same as the adiabatic process, which says P1 V1 minus P2 V2. There gamma minus 1. Here it is N minus 1. And the heat flow expression is just you have to multiply this factor to the polytropic work done. What is that factor? That factor is gamma minus n divided by gamma minus 1 into polytropic work. So what is polytropic work again? It is P1 V1 minus P2 V2 divided by n minus 1. So the cumulative expression for calculating the heat flow in a polytropic process could be gamma minus n into gamma minus 1 into P1 V1 minus P2 V2 divided by n minus 1. And this was the recap of whatever you have studied till now. Clear? Any doubts?
No, sir.
Understood all the process, all the heat flows, all the work flows? Any doubts?
Yes, sir.
I'll be asking questions, that's why I'm asking. Any doubts? Everyone? Vignesh?
No, sir.
Vignesh? Varun? Sujan?
No, sir.
Varun? Sujan? These two people are not
No,
there.
sir.
Hazim? Devdarsh? Hazim and Devdarsh. Total 4 people. Bharat?
Yes, sir.
Devdarsh, understood? All the 5 process, workflows and heat flows. Devdarsh?
Yes, sir.
Understood all the 5 process, workflows and heat flows?
Yes, sir.
Great. So today we will be discussing the most important ever repeated. So it is being repeated all the way in your examinations. Only few examinations it is not been asked. Such an important question, which is known as the steady flow energy equation. So did you call my name? Yeah, Hashir, no, I did not call you. So the steady flow energy equation, shortly known as SFEE, is damn important for your internals, for your externals, as well as for your ATD subject also. So that is the importance of this particular thing. So we'll be discussing in brief again. Okay. I'll be discussing in brief, so just concentrate. In an open system, a substance usually is filled with a fluid, okay, point-to-point solid contact, steady flow, intermediate is continuous. Okay, it's better to read. Sujan, can you just read up this?
Okay, sir.
Hmm.
In an open system, a substance, usually a fluid,
Hmm.
So that fluid after across
Crosses. Hmm.
crosses system boundary in
Hmm.
one or more places, the fluid may
Yes.
enter or leave the system. In
Yes.
addition to the
Hmm.
possibility of heat and work transfer,
Transfer.
at one point has at
Several
several
point.
points.
Okay.
Next,
The
the
fluid
fluid
flows.
to a system either at steady state or may flow intermediately, not
Intermediately.
continuous.
Not
To
continuous.
analyze
Yes.
uh, to analyze such system, control volume concept is to be introduced. It is the region in the space upon which our attention
Attention
is
is focused.
focused.
Okay. So that is what we have dealt about the control volume concept, is it? So what is a control volume? A control volume is that particular region of space where you focus all your studies into and just try to analyze that particular part of your system. So that is known as a control volume concept. In that case, so suppose if you have a pipe which is shown here like this, in this pipe, if the water is flowing at a lower pressure, what happens? The water might be full. The water might be full at this section. Later, it may be intermediate at this section. Again, it might be full at this section. So if you consider whole of a system to be analyzed, so what happens is it makes the things complicated. Rather, what we'll be doing is we'll be selecting a particular portion of a system like this, and we will try to analyze only within this particular aspect. So that is known as a control volume concept, and that particular concept is being used in order to derive your steady flow energy equation. Next, Varun. Bharat. Bharat. Ritesh Kumar.
Yes, sir.
Yes, Ritesh. Carry on with us.
What's it?
Just read from
Which one,
here.
sir? That most and most of
Yes,
engineering.
yes.
Most of engineering equipments cover flow devices which need to be analyzed by the concept of control
Control
volume.
volume, that is what I have just said. So in order to analyze, certain assumptions are made, Ritesh. So what are those assumptions? Just read out and say as.
In a steady flow of system, following assumptions are made. The
Yes.
state of fluid at each point in the control volume does not vary both 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 time or both
With the time, it is not
with time.
with it is with the time. Okay,
With
fine.
time.
So what do you mean by a state? State is nothing but its pressure, its volume, and its temperature does not change with respect to time. That was a simple assumption. Second assumption, Pritesh.
Net amount of heat and work entering the control volume for
Volume,
a specified unit
time.
time.
Hmm.
Time must be equal to sum of net amount of the heat and work leaving the control volume for the some interval of time.
Of
The
the
most
same interval.
the same.
So what does it mean? Means suppose if you have considered this to be a control volume here, okay, in this control volume or treating this as a system, what happens? The amount of work and amount of heat exchange which is happening at the inlet should be same with respect to the outlet. If suppose 10 kilojoules of heat interaction happened at the inlet, same 10 kilojoules of heat interaction must happen at the outlet. That is what the meaning of the statement, provided both has a same time gap. So this is measured for 10 minutes. In 10 minutes, for 10 kilojoules. Here also in 10 minutes, 10 kilojoules of heat interaction should happen. So that is the assumption. The next one.
The mass flow rate at the inlet and outlet of a control volume must be constant.
That's what.
The
So
mass
even if your work and heat interactions at inlet and outlet are same, even the mass flow rate, amount of liquid entering the system and amount of liquid leaving the system, even that particular thing has to be constant. Yes, next one.
The control volume does not move relative to the coordinate frame.
Definitely not. Suppose if your control volume, suppose you take this particular control volume here, if it is moving like this, so how will you make your analysis onto the system, man? It is definitely not possible. So your control volume should not move either. Rather, it has to be fixed at a certain position. So that is what the assumptions is being made. And the last one,
The fluid is uniform in its comparison, the comparison or composition,
composition.
composition and will not charge will what is that sir?
Change.
Change
Change its
its
chemical
chemical
composition,
composition.
will not change its chemical composition. So I think this particular point is very much clear. The composition or the chemical composition of the fluid should remain constant throughout its flow. That is what it's meant. Next, Siddesh PN. Siddesh.
Sir. Sir.
So he has given a theoretical concepts. Why and what do you mean by a steady state? So can you just read that particular thing which I have marked in the flow bracket?
When a system executes in steady
Exactly.
state, state
Particular
at a particular location, that thermodynamic properties
will have
will have the fixed value and will null
not
change
change
not change
with
with respect
respect
to
to time.
time.
Hope it is clear, man. What do you mean by steady state? Sujan, what do you mean by steady state? Sujan.
Thermodynamic properties will be fixed.
Exactly. So thermodynamic properties will not change with respect to time. If it is not changing with respect to time, then you are in a steady state. So let us go into the steady state energy equation now. Consider the steady flow system which enters and leaves the system as shown in the figure. So this is the steady flow device which we are talking about. Here it is the entrance through which the flow of the fluid is entering the system, and here is the exit port where the flow is getting out of the system. This particular device might be anything, man. It might be your turbine, it might be your compressor, it might be your pump, or any other device. For all such equipments, we have just named it as a steady flow device. It could be anything. So later, once we have derived the steady flow energy equation, we will be applying that particular equation for different engineering applications. As I mentioned, it might be your turbine, compressor, pump, boiler, expansion valve, throttling valves. All those are equipments. For every individual equipment, we will be applying whatever we have derived, which is known as the steady flow energy equation. We shall see in that. And this is the datum height, man. This is the height from the ground level, that is known as Z1 here. And this is the height from the outlet height from the ground level, which is known as Z2. Okay. The properties are the steady state with respect to time and location, and the control volume and the mass energy will not make relative. That is not nowhere required. Let A1 and A2 be the cross-section area of the stream at the inlet and outlet respectively. That means the area is talking about the area of cross-section. So this is nothing but A1, and the area of cross-section at the outlet is known as A2. And m dot 1, so this is m dot, guys, m dot 1. So if you just write m1, it is mass at state 1. If you write m dot 1, then it is mass flow rate at state 1. So what is difference between m and m dot? Sushant, what is the difference between m and m dot?
Yes, sir. It's mass flow rate, sir. M dot into 1 means.
Yes, so m dot is nothing but your mass flow rate. If you just write m, it is the mass.
And
Very good. Okay, so the mass flow rate at the inlet and outlet, which is measured as kgs per second, the mass flow rate, of course, the time would come. P1 and P2 be the absolute pressures at state 1 and state 2, that is, U1 and U2 be the internal energy at the inlet and outlet respectively. H1 and H2 be the enthalpy at inlet and outlet respectively. And C1 and C2 are the velocities at the inlet and outlet, the velocity at which the fluid is moving, is it? If it is moving fast, that is so. Usually what happens, the velocity is taken as V, right? In the physics. We take it as V over there. But here I have taken it as C, wantedly. Why? Because you should not get confused between V and C, because V is already we have taken it for the volume. Yes or no? So if you take for the velocity also, so you might get confused. So that is the reason I have taken just the value of C, which is indication of the velocity. C1, C2 in the sense C1 is the velocity at the inlet, C2 is the velocity at the outlet. Okay, as simple as that. Next. Z1 and Z2 are the elevations above the reference plane I have just mentioned, that will be in meters. And Kev is the net heat transfer through the control surface. So whatever heat is getting transferred to the control surface is Kev, and W is the net work transfer through the control surface, and T is time in seconds. And the principle of conservation of mass is given by M1 is equals to M2. What does it mean, guys? It's very easy. See, suppose if 10 kgs of fluid is entering inside the system, like this, through the inlet, that is state 1. So how much kg should I expect at the outlet?
10 kg.
10 kg, is it? So
10
that's
kg.
why I say M1 is equal to M2. That means this particular law is nothing but your law of conservation of mass, which says whatever the mass which is getting inside the system, the same amount of mass should be get it back from the system. So that is known as law of conservation of mass. From that, we have taken it as M1 is equals to M2. In the same ways, I am applying it for the mass flow rate, which is mass flow rate at the inlet is equals to the mass flow rate at the outlet. There is no accumulation of mass within the control system. If you're sending the 10 kg, you should get back 10 kg. Suppose 2 kg yellow hoki middle ಅಲ್ಲಿ ಸಿಕ್ಕಾಕೊಳ್ಳಲ್ಲ. ಹೌದು ತಾನೆ? So if you're sending the 10 kgs, definitely you should get 10 kgs back. Okay, there is no addition or deletion of mass in that particular case. Okay. The principle of conservation of energy states that the rate of flow of energy entering the controlled volume must be equal to the rate of flow of energy leaving the control volume. So if it is true for the mass, it should be true for the energy also. So I said about the 10 kg, which is the mass. Now I talk about the energy. If there is a 10 kilojoules of energy interaction at the inlet, so even there has to be 10 kilojoules of energy interaction at the outlet as well. So this is what the law of conservation of energy states as. Okay, so in that sense, I have just written the law of conservation of energy applications. What is M dot 1? What is M dot 1? It is the mass flow rate at 1. What is E1? E1 the energy at 1. And M dot 1, again, I have said you it is a mass flow rate at 1. P1 and V1 are the pressures and volumes. And Q is the heat interaction. That should be equal to the outlet. Same thing, M2, E2, and P2, E2. So this particular thing should be equal to this particular thing according to the law of conservation of energy, where this are there, right? E1 and E2 are the two new factors for you. Rest all you know. You know what is Q, you know what is W, you know what is M, you know what is P, you know what is V. But the new factors are these factors, E. So how does we define it? So that particular in total energy, so internal total energy E is a summation of these three energy, guys. Okay, the energy, which is the total energy, is a summation of the kinetic energy, the potential energy, and the internal energy. So what is kinetic energy? I think 99% of you would know that. What is kinetic energy? What do you mean by a kinetic energy? Is Vaibhav? Vaibhav? Darshan is shitty. Darshan is shitty. Chirant Jain. Chirant Jain. Anish Pinto.
Yes, sir.
Chirant, so what do you mean by kinetic energy? Nish Pinto. So what do you mean by kinetic energy? Energy associated with the moving particle, that is known as kinetic energy. Energy associated with the object at a certain height is known as a potential energy. Yes or no, man? Everyone.
Yes, sir.
Yes, sir.
Kinetic energy and potential energy, guys. Kinetic energy is nothing but energy associated with the moving mass. So if it is moving at a velocity c, how will you calculate its kinetic energy? It is half mc square, right? This is all you have learned. And if the certain mass is at a height of h, then it poses a potential energy. So that particular potential energy is measured as what? mgh. I think all of this you have learned, right or wrong? Yes or no, man?
Yes, sir.
Yes, sir.
The same thing I am applying here. See, total energy is the summation of kinetic energy, potential energy, and that's internal energy. So internal energy is for BTT, that I will take care. So kinetic energy is what? Half mc square. Potential energy is what? mgz, because we have not taken h there, because h is meant for enthalpy in the BTD. So that's why we have taken z. Z is known as a datum height here. So mgz plus q. So in that case, if I take it for the unit mass, it could be c square by 2 gz and u. Why? Because I have taken for a unit mass. So mass is unity over there. So if I apply this particular thing for the inlet and outlet, it would be as such one. So C is C2 square by 2 plus GZ plus U. Apply for the inlet. It is C1 square by 2 plus G into Z1 plus U1. This is not C1, it is U1. It's U1. Okay, and this is U2. Okay, so that is your total energy. So what is total energy, Hashir? How many energy does it contain? Hashir?
Yes, sir.
So how many types of energy does total energy contain?
Kinetic energy, potential energy, and internal energy.
So this we have derived for inlet as well as for the outlet. So going back to the equation number 1, here you have the value of E1, here you have the value of E2. Just substitute the things, man. So E1 is sorry. I'm sorry. So E1 is substituted as this particular thing which you have derived here, and E2 is substituted as this particular thing which we have just derived. So just multiplying the things, and before you multiply, you substitute U1. So what is U1? Remember, it is as H plus PV, U plus PV. Remember or not? So the same thing you have substituted here. It is U1 plus P1 and U2 plus P2 V2. So once U1 plus P1 V1 is H1 and U2 plus P2 V2 is H2, what we can do, you can just assemble this and substitute as enthalpy, and here also you can assemble this and substitute it as the enthalpy at the outlet. Okay, so when you arrive at the final equation, it is this particular equation what you get. So that is m dot 1 into c1 square by 2 plus g into z1 plus h1 plus q is equals to m dot 2 into c2 square by 2 plus g into z2 plus h2 plus w. So this is the steady flow energy equation. I give you exactly 3 minutes to remember and mug up this particular equation. I may ask anyone, and your time starts now. Okay, learned. Stephen.
Yes, sir.
What is the equation? Steady flow energy equation.
M1 into
Hmm.
C1 square
By
divided by
2.
2 plus GZ1 plus H1
Hmm.
plus Q minus M2 into
Minus.
C2
It is not minus, guys. It is equal to, man. Is
CN
equals
square
to.
C2 square divided by 2 plus GZ2 plus H2 plus W.
Very good. So next, Chirant.
Sir.
Give me the steady flow energy equation. John Rai.
Yes, sir.
So give me the steady flow energy equation.
M1 into C1
Mm-hmm.
square by 2 plus G Z1 plus H1 plus Q is equal to M2. M2 into C2 square by 2 plus GZ2 plus H2 plus W.
Yes. Hashir.
M1 into C1 square by 2 plus GZ1 plus H1 plus Q equal to M2 into Cn square by 2 plus GZ square plus H2 plus W.
Okay. Swaroop.
Yes, sir.
Give me the SFEE.
M1 of C1 square divided by 2 plus GZ1 plus H1 plus Q equal to M2 of Cn square divided by 2
It is
plus
not
GZ2.
CN1, it is C2. It's C2.
Okay, C2. Yeah. C2 square divided by 2 plus GZ2 plus H2 plus W.
Okay, great. So hope you have got the things. Applying energy conversion equation, that is steady flow energy equation, now which will apply for the multiple inlets and the multiple outlets. Man, for multiple inlets and the multiple outlets, the continuity equation is given as, see, whatever is being inletted, the same thing has to be outletted. That is the funda, right? So if there is a body like this, and C1 amount of fluid is flowing with the density ρ1, and the area of cross section is A1 at the inlet. If there is an outlet with an area of cross section A2, C2 amount of fluid is flowing which has the density of ρ2, then A1 C1 ρ1 must be equal to A2 C2 ρ2. So that is known as the continuity equation. It is derived from the law of conservation of mass, which says M1 should be equal to M2. If you cumulatively multiply all these three, you'll get M1. Okay, so that's why the continuity equation says what? It says A1 C1 ρ1 must be equal to A2 C2 and ρ2. So this is the continuity equation. That's fine. Now, suppose if you are applying it for SFE for this particular thing. So in this particular thing, how many inlets are there? Yes. How many inlets are there?
2.
There are two inlets,
2.
which is this and this. Okay. That's why here is your is equal to sign. Okay. Here is your is equal to sign. Hope you found that. Yeah. Here. Here is your is equal to sign. So since there are two inlets, which is M1 dot and M2 dot, for both the things, you have to apply the energy expressions, which is M1 into H1 plus C1 square plus 2 in plus G into Z1. That is for the M1 dot. And for this particular segment, the second inlet, which is M2 dot into H2 plus C2 square by 2 plus G into Z2 plus Q. Okay, this is for the inlet, that is fine. Now for the outlet, how many outlets are there? How many?
2.
So here also there are 2, but outlets are M3 and M4. Same thing if you apply M3 into H3 plus C3 square by 2 plus Z3 into Z plus M4 into H4 plus C4 square by 2 plus Z4 into G. So applying it for the outlet plus W. Remember, always K is attached to the inlet and always W is attached to the outlet. Okay, so this is how you apply the energy conversion equation. I mean to say the steady flow energy equation. Similarly, if you apply the law of conservation of mass or the continuity equation, so inlet says M1 here, M2 here it is outlet is M3 and outlet is M4. Whatever it is getting in, the same has to be got out. So it is M1 dot plus M2 dot should be equal to M3 dot plus M4 dot. Yes or no? According to the law of conservation of mass. Is that true? So if it is true, then this is how you apply. So M1 plus M2 must be equal to M3 plus M4. I told you M1 is A1, C1, rho 1. So similarly, if you apply for M2, M3 and M4, what you'll get? A1, C1, rho 1 plus A2, C2, rho 3. Rho 2 is equals to A2, A3, C3, rho 3 plus A4, C4, rho 4 and so on. So how many inlets and outlets you have? If you have an inlet, just add it to the LHS. If you have an outlet, just add it to the RHS. There you're done. So this is the application of SFEE and the continuity equation. Okay. So this will be knowing very detailedly in case of problems. When you're solving the problems on this, you'll be having a detailed study of that. Okay. Now, I told you, once you derive the SFEE, we shall look into the systems and try to apply the SFEE for the different systems now. So, first category of the systems are known as the work absorbing devices, in the sense compressor, pump, and various. So you need to work on the system so that your system absorbs your work. So those are work absorbing devices. Now, what are work developing devices? Can you name few which gives you the work? Work developing devices. Can you name few? I have named the work absorbing devices to be compressor and pump. What are work developing devices? Any examples? Turbine, excellent. Turbines, very good. Next.
Motor.
Huh?
Motor.
Superb. Even motor can be considered as a work generating device or a developing device. IC engines is an excellent answer. Very good one. So we shall just directly go into the application of SFEE now. See, here is your inlet. This is your compressor. What happens in a compressor? The air gets in, it gets compressed, the pressure gets increased and gets out. So this is what happens in the compressor. Simple statement. So here you're working work on the system. So work is done on the system. That's why it is. If the work is done on the system, it is positive or negative.
Positive.
If it is work done on the system is not giving you work freely. You should work on the system. Then it is positive or negative?
Negative.
Negative. So system is giving you the work, then it is positive. If system needs work, you should spend work on the system, like as of a compressor. You should work on the system. If you are working on the system, then it is negative. Okay, the same thing. In this case, so this is the datum height, suppose Z1, and this is the datum height, say Z2. Okay, let us see how the application is being done. In this compressor, the potential energy and the kinetic energy is ignored. If potential energy and kinetic energies are ignored, where is the potential energy segment, man? Which is the potential energy segment? Whether H1 is a potential energy segment, whether Cu2 square by 2 is a potential energy segment, or GZ1 is a potential energy segment. Which one is the potential energy segment here? Hello? Yes, man. Which is the potential energy segment here?
That one.
But the energy saver automatically switch on, and you can see the where there is no switch on bulb, so you can see this.
Okay. So which one is the potential energy component or a segment? I think this one, G into Z1, right? So that is your potential energy component. Yes or no? Yes or no, man?
Yes, sir.
So which is the velocity component? I mean to say the kinetic energy component, which is this. He says the potential energy and the kinetic energy are ignored. That means the both of things will go to zero because this is the potential energy and the kinetic energy are being ignored. So W is negative, you have to remember, because you're working on the system. The system rejects heat. That's why Q is also a negative. For an adiabatic device, suppose say I treat this to be an adiabatic device. So what is the heat flow in case of an adiabatic device? What is the heat flow in case of an adiabatic device? So it is zero. That's why if I treat the system to be an adiabatic device, the Q also will turn to zero. So whatever the remaining things are there, you can just note it down. If in the question paper, he has asked to apply the SFEE for the compressor, you should draw this diagram, write a description, what does a compressor do, and you have to mention this: the potential energy is ignored, work done is negative, system rejects heat, and the adiabatic device, so Q is zero. So you have to write the SFE statement and mention all the components which are zero, and remaining whatever it is there, suppose m dot is remaining here, H1 is remaining, and H2 is remaining, and W is remaining. You have to rewrite that expression and put it in a box and close the answer. Any difficulty in doing so?
No, sir.
Easy, right? Same thing for the different equipments, it will go on, man. Suppose go to the centrifugal pump here. What does a centrifugal pump do? What is the function of a centrifugal pump? In a centrifugal pump, the water will be at the lower level. You are working on the system, that's why work is negative. Okay. And see, if water is pumped and its pressure is increased, and the potential energy of that particular system is being increased because it is taken toward atom height of Z2. Okay, that is what's the function of centrifugal pump. You have to see what all is there in centrifugal pump. Work done on the system, so it is negative, right or wrong? Here the work is done on the system, that's why it is negative. He has given in the notes. Is it right or wrong?
Right, sir.
Right. Whether in the centrifugal pump, which is the pump in all of your home, you will be having that centrifugal pump. Whether in that centrifugal pump, do you play with heat? Does the heat have
No, sir.
anything role there? That's why your heat transfer is zero. That's why I can take Q straight away zero. Next, as the water remains same, the change in the internal energy can also be neglected. Is it?
Yes,
Because
sir.
the temperature of the water is not changing. If the temperature is not changing, your internal energy is only dependent on temperature. If temperature changes, only then your internal energy would change. Yes or no? So if the temperature is not changing, automatically your internal energy, change in internal energy is also zero. Now if you apply the steady flow energy equation, just write down the steady flow energy equation, extract this. So H1 you have written as U1 and P1, and H2 it is written as U2 and P2. Q is zero and work is negative. Only if you make certain changes, that forms your application of SFE for the centrifugal pump. Any problem in doing this? Any problem? Understood?
Yes, sir.
Understood? Okay. Now,
Yes, sir.
coming to the steam turbine. See, steam turbine is exact replica, a mirror image of a compressor. Okay, there you work on the system, but in case of a steam or a gas turbine, the work is expected from the system. That means the system gives you the work. That's why the work done is positive over there. The same assumptions can be made here, which is known as kinetic energy and potential energy are neglected. Okay, the work done by the system, so it is positive. The expansion of the fluid in is assumed to be adiabatic. If it is an adiabatic process, what happens to the value of Q? What happens to the value of Q if it is an adiabatic process?
0.
So it is zero. Same thing is substitute in the SFEE. So potential energies and kinetic energies both are neglected. Q is neglected. Why? Because it is an adiabatic process. Whatever it is remaining, W will remain positive anyhow. So just substitute, and that is an expression for the application of SFEE on the turbine. Let us look into the another equipment, which is known as a nozzle. So what does a nozzle do? It varies, it converts the pressure into velocity. Okay, if there is a pressure, a huge pressure at this particular thing, this particular frame, what happens? The nozzle will pinch it up and your velocity gets increased. Your velocity gets increased and pressure drops. So that is the function of your nozzle. So you can write the short description, what is the nozzle and whatever it is neglected or accepted over there. The work done is zero, absolutely. Is there any work done here in this entire nozzle session? There is absolutely no work done there. Changes in the potential energy can be neglected. Why? Because your inlet and as well as your outlet is at the same datum height. So inlet and outlet are at the same datum height. That's why it is neglected. Due to perfect insulation, see, you're providing a good insulations to the nozzle, then there will be no heat transfer. So that's why QO can also be neglected. Enthalpy decreases and kinetic energy increases that happens in the nozzle. So if you apply a steady flow energy equation, what all will go zero is G into Z1 and M dot 1 will be equal to M dot 2. Why? Because there is no change in the mass, so you can easily neglect, and Q and W will go. So the remaining aspects are H1 plus C1 square by 2 in the LHS, H2 plus C2 square by 2 in the RHS. So you can form this particular expression from that, which is the application of SFEE for the nozzle. Okay, I think it is time, right? Still, there are few more. Boiler is there, throttling process is there. And there is a problem. Okay.
ಸರ್ ಇದು ಎಸ್ ಎಫ್ ಇ ಎಲ್ಲ
SFE
ಇಂಟರ್ನೆಟ್ ಸಿಗುಂಟಾ?
internal ಸಿಗುಂಟು.
Okay, sir.
Okay, so we shall look into the next class, man. How many are there? 47. Okay, let me take the attendance then. Okay, so few more SFE applications. After that, few more problems are there. We'll complete the module very fast. Any doubts in today's class? The derivation of SFE and the applications of SFE for 2 to 3 equipment. Still 2 to 3 are there. We shall discuss anyhow. For that particular part which is covered in the today's class, any doubts you have? Anything need to be discussed? Okay, guys, so we shall do one thing. I will just take the attendance online. Where is that link? Okay, so I have taken the attendance online, those who are present, and the time also will be noted down. I'll mark the attendance from that since it is time. I don't want to waste your time. Okay, we shall meet up in the next class. In the next class, we'll discuss some more applications of SFE and the problems on that. Okay, till then, take care. Have a nice day. Bye.
Thank you.
Thank you.
Yeah.
Thank you,
Sir,
sir.
Thank you, sir.
Thank you,
Thank you.
sir.
Thank you, sir.
Thank you.
Yes, yes. Don't worry, your attendance will be taken online. Okay.